In this video, I am going to discuss a new concept related to partial differential calculus, that is Jacobian. Let u is a function of x and y and v is another function of x and y. Then the determinant del u upon del x, del u upon del y, del v upon del x, del v upon del y is called Jacobian of u and v with respect to x and y, and which is denoted by del bracket u comma v upon del x comma y, or capital J u comma v upon x comma y. As for example, u is equal to x square plus y square plus 2xy, and v is equal to x cube plus y cube plus 3xy square plus 3x square y, and we need to find out Jacobian of u and v with respect to x and y, that is del u comma v upon del x comma y. So first we have to differentiate equation number 1 and equation number 2 with respect to x partially. Differentiating 1 partially with respect to x, we get del u upon del x, that is the partial differential of u with respect to x, and this is the differential of u taking x as variable and y as constant. So first term x square, which is considered to be variable with respect to x, so differential of x square with respect to x is 2x, and the next term is y square, which is purely constant term because this is differential partially with respect to x, so y is taken as constant, so its differential is 0 plus 2xy. Here y is considered as constant and 2 is numeric constant, so there is only one variable, that is x, and its differential is 1, so partial differential of this term with respect to x is 2y. So simply we may write it as 2x plus y, make it equation number 3. Similarly, partial differential of u with respect to y, we may find del u upon del y is equal to 2y plus 2x or 2y plus x. Equation number 4. Similarly, we may find the partial differential of v with respect to x, del v over del x, that is 3x square. Differential of y cube is 0, and the differential of 3xy square is 3y square, and differential of 3x square y with respect to x partially 6xy. So here we may take 3 common. In the bracket we have x square plus y square plus 2xy. So we may write it as simply 3x plus y whole square. This is fifth. And del v upon del y. So here x cube is constant because it is a partial differential with respect to y. So and the terms of x is considered to be constant. So the partial differential of x cube with respect to y is 0, and partial differential of y cube is 3y square plus here 6xy plus, and here 3x square. So we may take 3 common out of it, and we have y square plus xy, 2xy, sorry, plus x square. So if you observe, this is also x plus y or y plus x whole square. So this is equation number 6. So now we may find Jacobian of u and v with respect to x and y, which is simply determinant del u upon del x, del u upon del y, del v upon del x, del v upon del y. So this is equal to determinant. Now substitute the value of del u upon del x, del u upon del y, del v upon del x, del v upon del y here from equation number 3, 4, 5 and 6. So we have determinant 2 x plus y, 2 y plus x, and 3 x plus y whole square, and 3 x plus y whole square. And as we know that we may take anything common out of any row or any column. So if we see from the first row, the whole 2x plus y expression is common, and from row 2, the whole expression 3x plus y whole square is common. So if we take 2x plus y common out of R1 and 3x plus y whole square from R2, we get 6x plus y whole cube, and the determinant left 1, 1, 1, 1. Because by the property, if the rows, any two rows or any two columns are identical in a determinant, its numerical value is 0. So as we see that both the rows, or we may say both the columns, are identical of this determinant, so its value is 0. So we may write it as 6x plus y whole cube into 0 is equal to 0. So Jacobian of u and v with respect to x and y in this case is equal to 0.